Okay, welcome everyone. Today is our second episode of our CAD modernization series. Thank you all for joining. I hope you've all got your coffees ready and ready to learn a bit about advanced assembly and how we can better manage our large and complex designs and better enable our workforce to work on those designs throughout the design process. So let's start off with a little bit of housekeeping and whatnot. As I said, today we are running through the second episode of our CAD modernization webinar series. 2 weeks ago, we ran through the design packages of what's available in our current Creo offering. So if you missed that or wanted to catch up on that, that is available on demand on our website. So do check that out. And also available on our website is the ability to subscribe to our future episodes. So on the 4th of June, a colleague of mine will be running through simulation-led design. So how can we leverage simulation earlier on in our design cycles and therefore get better designs out the back of that design cycle. Then on the 18th of June, I'm going to be back and I will be running through Creo 12, what's new in that new version of the software. So as I said, that is available online. Please head over to our website and get subscribed to those. And we'll see you then. Little agenda for today then. So I'm just going to again do a little bit of an overview of myself and PDS Vision for those that maybe are new to us. I'm then going to take a look at and talk about some of the assembly challenges that we see. So a lot of our customers have similar challenges when it comes to working with complex designs, complex assemblies, working in teams, these sorts of things. So we'll address those and talk about how advanced assembly as an extension for Creo can help with that. We'll then talk about some of the key capabilities and concepts of advanced assembly with some demonstrations, wrap up with a few bit of final value, and then obviously we always have some time for Q&A and that sort of stuff. So please do leverage the question functionality within GoToMeeting. I will answer those at the end. And also, if you have any other questions, please feel free to leave them and we'll get to those. A little bit about myself. My name is Rory Island Bocott. I'm a customer success manager here at PDS Vision. I've been here for just over 10 years and I come from a tech background. So I've worked with a good portion of the PTC products that we offer at PDS Vision, including CAD, augmented reality, PLM, and our IoT suite as well. So fairly broad knowledge set across the PTC product range. But it's my job really to ensure that you, our customers, are getting the most out of the software you are purchasing from us or have purchased from us in the past. So presenting these sort of webinars, going out, delivering demonstrations to customers and ensuring you're getting the maximum value and ROI from the products that we offer you. PDS Vision then, as a whole, we're a global business. We span 16 different locations across the globe, over 500 employees, with over 300 of those being technically focused. And we offer the entire PTC portfolio and to provide services and support for those products, as well as the ANSYS portfolio, the simulation portfolio as well. We also have our own subset of products within the MyPDS suite, and these are really products that are designed to add additional layers of functionality and value to the PTC offering. Okay, let's start then by positioning some of the problems that we see and the challenges that our customers face when working with more complex products, larger assemblies, and larger design teams as a whole, really. So with these complex products comes a variety of sort of different challenges. As assemblies get larger, maybe and teams get larger and maybe more distributed, especially these days when we've got people working from all over the place, managing all of these pieces in that puzzle that we call our sort of designs can become a real big headache. And more traditional and basic workflows start to fall down after a certain scale. They're not particularly scalable if you're sort of leveraging early design techniques that you sort of learn when you first come into the CAD environment. And I'm sure a lot of those issues that you can see on screen will be familiar to a lot of you. Things like too many parts, or you've got too many people with maybe a lack of defined structure in your designs. You can have models taking a long time to load, teams struggling to collaborate with each other, working on other people's data when other people want to be getting on with their own things, these sorts of situations. And you can also end up with them with managing these design changes. What happens when you want to make a change to these really complex products? You end up with a sort of a puzzle of dependencies, fail regenerations, and just headaches overall, really. So if these are resonating with you, you're not alone. This is something that's been not a problem. We have tools to solve the problem, which is a good thing. That's something we're going to talk about. But you're not alone. A lot of our customer bases work on big, complex data. It's one of Creo Parametric's real strengths, is working on these large assemblies. And we are one of the best, if not the best, when it comes to working with large data sets. So we've got really good tools to help you work with that. So let's introduce advanced assembly then to you all. I'm sure we have a range of expertise on the call, but let's bring in some of the basics here to start with. First of all, then, advanced assembly, or AAX for short, is an extension for Creo Parametric. Okay, and you can get your hands on it in two ways, really. You can either purchase it as an extension for Creo in a locked or a floating license, and you can have that. Or you could opt for one of our higher tier packages. So you can have Creo Parametric on its own, or you can opt for a T2, 3, T4 license, which comes with advanced assembly. So you can get hold of it in one of the two ways. Probably worth noting, I mentioned it on the last call as well. We actually have an offer on at the moment for those users that are looking to upgrade an older version of Creo Parametric to a newer version. We have a T2 offer, a discounted offer for upgrading to a T2 license. That may be of use for some of you out there if you're looking to upgrade currently. But let's start then by talking about a design methodology, something that we call top-down design. So if you're used to building your products in a certain way, maybe you're building your parts first and then assembling them together, that's something that we call a bottom-up approach. Okay, you're working at the small level and then building up larger beyond that. And this approach is really good. It's quick, it's fast, and works really well for simple designs. But when you're starting to deal with larger designs, larger assemblies, more complex assemblies, or you have more people working on your products, that approach begins to fall apart a little bit. You have parts being designed in isolation that don't communicate with each other. Changes can behave unpredictably, and it becomes a bit of a headache to implement those changes because you've got loads of different parts you have to modify. And coordination really becomes a bit more of a challenge. So top-down design kind of flips that on its head. And what we do is we start off at the top level, at the overall assembly level, and then work our way back down through the model. Okay. And when you kind of think about it, this approach really kind of makes sense because all of your design requirements, well, not all of them, but some of the major design requirements for a product are at this top level. If we take this bike on screen, for example, some of the design requirements might be things like wheelbase, and how long is the wheelbase? What's the ride height of the bike? What's the rake of the front forks? These sorts of things. And if you had to make a change to one of those requirements, you don't want to be playing around with all the individual components in order to accommodate that change. What you want to do is make a change at that very top level and have all of your lower level components update to accommodate for that change. And that's really what top-down design is about. It's enabling a workflow with a set of tools that means you can start at this top level and have that information trickle down through your model, freeing people up to work on whatever it is they're working on. Okay. So this approach really helps manage complexity in these complex products. You improve communication through the logical sharing of information to users. It enables people to work on their own separate areas of a design without stepping on each other's toes and those sorts of things. And I think it's probably worth saying, as I said, it's not a feature. With top-down design is not a feature in Creo, but we have a set of tools that enable this workflow, this sort of logical approach to more complex design assemblies. Along with that, then we have something that we call concurrent engineering, and you'll hear PTC talk about this a lot. And concurrent engineering is all about teams working in parallel, okay, rather than working in sequence, okay. So in a more traditional process, you have this sort of linear process where people carry out work one after the other. You end up with teams waiting on other teams to finish work. before they can start on their own. You get parts being designed in isolation, and from that you get miscommunication and all sorts. So by leveraging some of these top-down design techniques, which we're going to go into more detail, you enable your workforce to work together all at the same time on their own individual elements. So in this scenario here that we've got on screen, where we've got Sarah working on the engine casing, Billy working on an engine block, in a more traditional workflow, or on a bit of a bottom-up approach, one person has to finish their work before someone else can work on theirs, because we all need this information in session. With a top-down design approach, we can share the right information to those users. So we can share all the information Sarah needs to build the engine casing in context with the overall assembly, so she can work on that. And we can share the right information to Billy to work on the information that he needs to complete the engine block. Maybe key interfaces, component locations, those sorts of things. We can distribute that out to everyone, and they can all work on their own information at their own time. And so that's concurrent engineering. It's being able to have your teams all working at the same time on the areas that are important to them. So what I want to do, I sort of almost jump straight into a demonstration here. I want to talk through some of the capabilities within advanced assembly and show you some of these workflows. And I've kind of split things up into two sections. I'm going to talk a little bit about the advanced assembly workflow, so top-down design, skeleton models, which I'm going to dive into a little bit more detail on, sharing geometry across teams and different aspects of the design. And then we're going to talk about maybe managing that data as a whole itself, performance improvements, things like that. And we'll touch briefly on those. But just before we hop into a demonstration, let me just talk over some of the key factors here, because again, I think we might have a range of knowledge on the call. So this top-down design approach, at the heart of it is what we call the skeleton model. And you can think of a skeleton model as like a blueprint for your design. Okay, within that blueprint, that skeleton, we can build in design intent. We can include reference geometry, like interfaces between components, maybe through the use of surfaces. We can build in key dimensional information. So for this helicopter, maybe it's the distance between the main body and the tail rotor, those sorts of things, those key critical design and dimensions. And we communicate all of this information through things like 2D sketches, surfaces for interfaces, and maybe datum features like planes, coordinate systems for component locations. And so within this skeleton, we have sort of an overarching requirement for our design. And what we do is we take this skeleton, or we take elements of this skeleton, and we share them. Okay, so I've got a team working on the body work for my helicopter. In my skeleton, I might have some key design language lines, okay, so that really emphasize the shape and overall design style of the shell of my helicopter. I share that with their design team, and they use those curves to build their surfaces off of. So we share that information, and people in our teams go off and build the information off of that skeleton, so they can work on their own little area in context of the wider design. We've also got things like being able to control how that information updates when changes are made, but we'll go into that in a little bit more detail. So you've got all of these people working on different parts of the design, all working off that skeleton geometry. So these are a real key tool within the top-down design workflow. Okay, so let's have a run through a bit of a demonstration. I might pause this video throughout. I wanted to keep the video fairly quick, but I need some time to explain a few concepts as we go through. So what we're working on here is a model of a boat. So one of our PTC's customers, we're working on their data set, and we're sort of going to adopt a couple of different roles within the workflow here. So what you can see on screen at the moment is a skeleton model. Within this skeleton model is some key feature information. So we've got surfaces to define the hull shapes, maybe coordinate systems to define locations. And this has already been mapped out. A skeleton model is just a part file. You're just creating surfaces and sketches like you would in any other component. So we don't want to spend too much time working on how we build these skeletons. They're just part files. But what we want to do is share that information. And we want to distribute that to our wider team. So maybe someone who's working on the hull of this boat, we need to get information to them. So we can do that in one or two ways. And one way is to create what we call published geometry. And that is a collection of data. So in this skeleton, I'm collecting a load of references that are going to be of use to the person designing this dragger board. Now, when we're creating published geometry and we're collating this data set, that has a few key advantages. When you're sharing data, you want to make sure people are referencing the right data. So published geometry gives you a location of how to do that. It also means that if you're sharing data amongst multiple people, you can ensure that they're all getting the same data because you've defined the collection of references. And also, if design changes happen, maybe you want to add some extra information for downstream use, you can add it to these published geometries here on the left-hand side. So you can see we've actually got multiple different published geometry sets, which can be shared out to different teams, different departments working on different aspects of this boat. Now, because this is a slightly more complex model, maybe than some, what we can actually do is, well, actually, let's first of all talk about this. You can actually control what people can and can't reference. So at the moment, what we're saying here is actually people could just choose published geometry for this level within the design. What I was going to talk about before, though, is sometimes it makes sense just to have one skeleton model, which sits right at the top of the model tree, okay, and you work off that one skeleton. Now, with more complex products like a boat or maybe a digger or something like that, if you have too much information in your top level skeleton, you end up with the same headache that you started with. You've got all of this information all in one location. So what you can actually do is have multiple skeletons within your assembly designs. So each sub-assembly can have its own skeleton. The idea being, with your top level skeleton, you have a very crude, basic understanding of what the design should be. And then as you work your way down into your lower level sub-assemblies, you have another skeleton that builds upon some information from the top level and adds more detail. So you're adding more detail the lower level you go within your design. And you can have as many as you like. Obviously, you don't have too many, but you can have as many as you like. So what we're doing now is we're activating a lower level sub-assembly skeleton, and we're going to go and grab that published geometry that we just created from our top level. So if we make a change at that top level, it's going to feed down to this lower level skeleton. Okay, so you can see we've got that copy geometry feature now in our lower level sub-assembly. So let's hide off our top level. We don't want to be seeing that. And now what I can do, I can start working on a component. I'm maybe taking on the design role now. I've got to do some work. And another method of copying geometry, rather than selecting published information, you can actually go in and choose individual information. So I can actually manually go and pick from my skeleton. And that's something that you get to determine in yourself, your own workflows. You can make logical sense of when you should be publishing and sharing data en masse or making local references like this. So what I'm doing, pulling some information across from my sub-assembly, and now I'm working on my part. So we've got sort of the main hull shape, these style surfaces here. We'll mirror these and we'll create a bit of material. So we'll merge the surfaces together, and we're just doing design work now. We'll thicken this out, give it a bit of a material to it, and we'll make some then further detailed design refinements on top of that. So we can go in and do some removals here, make some cutouts. And throughout this demonstration, there are a few features and things predefined, predetermined. We're not interested in showing you how to create extrudes and sketches. So there are some predefined things just to help with the speed of running through this demonstration. I'm sure you're all aware CAD becomes a little bit repetitive once you know the basics. So we've copied geometry from the skeleton now, and we've built that into a model. We can now sort of take the role of another user here. And what I'm doing, I'm just switching over to a different simplified representation. And I'm going to talk a little bit more about simplified representations a little later on. But for now, you can just think of it as it's just changing what's on screen. It's just bringing back some information that was already there and hiding some other information off. But we'll talk a little bit more about that in detail. So I can now adopt the role of maybe a different user. And this user is actually in charge of the water system within the boat, and they're building a water tank. But what I want to talk about here is how we can control updates. So when we're bringing data and using data from a skeleton, how do we control when that updates, when that changes and modifies? So building up this water tank, we're referencing that back plate, that grey plate in the background that you can see. We've copied some geometry from the skeleton, which determines where that plate is. And we're using that when we're building up this water tank. There are various different ways in which we can control how things update. So when the skeleton modifies, which we're going to have a look at in a second, what happens here for this user on this water tank? So what we specified is when we brought that data in, we've chosen to manually flag the information when it changes. So now we've designed our water tank, we've just added these few features. We'll go in and make a change to our skeleton, which is going to affect how this tank is designed, or the shape of this tank, I should say. So just a few Boolean operations there to get rid of some information. But now we're going to jump back up to our master skeleton. And because we've shared this data logically down the system, this design change is going to have an effect on our plate, on our tank, I should say. So we're changing where that reinforcement plate sits within the hull, which in turn is going to have an effect on our water tank. So when we hit regenerate, all of the geometry updates, and because we set a manual flag on the copied information, the user gets a notification saying, this feature is out of date, something's been modified, you need to go and have a look at it. So we can use things like the reference viewer, or something that's of more use maybe is this show differences tool, where we can view both the outdated and updated information. So on screen here, you can see the newly modified data, which is in the orange. And in the background there, you've got the gray data, which is the old outdated information. So this is where that surface used to be. It now sits here. So now the user gets to choose whether or not that update is pushed forwards. We can either reject it and maybe go back and make a change back in the skeleton to undo it, or we can accept it like we've just done. And because we use that as a reference data, our tank has now updated. What we also then just did is set that back to automatic. So a manual approach is one approach where you get to determine as and when this data updates, or you can have it set to automatic, and that just means when it's regenerated, everything just flows down. Just some control tools in there to manage this information. Again, we can now take on another role of a user. And in this role, this user's building up a bit of a bracket for the alternator here, just a mounting plate. And this is really just to show a couple of different techniques. You know, we've talked about copying geometry from one location to another, specifically within skeletons, and then copying information from a skeleton down to a part. But you can pick and choose your references. You know, here we're designing a mounting plate, and we've made a local reference there. The height of that mounting plate has been locally selected from the bottom of the bracket on the alternator. So your old traditional techniques are still applicable. You just need to be aware of when you're using them. Maybe this mounting plate is only ever going to be used in this version of this boat, so we don't need to worry too much about making those references. But you're not restricting your workflow. They're just extra tools that are available to you when you're working on these designs. So with that local design change, we can just see everything updates as you would expect. But we're using a copy geometry to match the bottom plate and follow the hull shape. So the next thing we're going to take, I want to sort of walk you through when we're talking about assemblies, is making design changes. And making a design change like we're doing here, we're putting some cutouts, some windows and some doors in this dividing panel in the interior of this hull. This design change can have a knock-on effect, which we'll take a look at. The positioning of these windows and holes is maybe going to affect another team. We have an interior design team maybe that are working on the interior, and we have maybe the interior infrastructure, the walls, the doors, and those sorts of things that are working on all of that information. Those two interplay, but they're different design teams. So how can we communicate what's happening from one team to another team? Well, we can do that using what we call a shrink wrap feature. So once this component's been modified and updated, we'll dive into a little bit more detail. We'll just apply the finishing touches here to this interior wall. So we've made a design change, and this user maybe works in a separate team, as I've said. We'll now swap over to a team that is focusing on the interior. So as you can see, with the interior, that design change of that interior surface that's been made by another team has an effect on this model. So how can we ensure that when this user is working on this model, the interior, that they understand when this design change has happened? At the moment, we have everything open all in one session, but if I was on the interior team, I should only really be using the information that I need. I shouldn't be pulling on all of this data, all these interior walls, because that's going to prevent the other team from working on that data. But we want to communicate that information. So what we can do, if we open up this model, and this is maybe what the interior design team are working on, in this skeleton model that they're leveraging, we have what's called a shrink wrap feature. Oh, sorry, I managed to reset the whole entire video. Let me skip back through to where we were. Let me open this back up. So in this model, we can see we have this shrink wrap feature. And what this is doing is it's going away, and I'm going to talk a little bit more about shrink wraps and how we can create them, but it's going away and grabbing this assembly, which is the framework or the interior walls here, and it's creating a skinned, lightweight version of that file. Okay, so it's opened it up, created a skinned version, and brought it into our skeleton model. What that means is we have a reference to that data without bringing all of that information into our session. So our design team for the interior can work on this in reference and understand what's going on in the rest of the design without using up all of those resources, all of those components and parts. And what that means is this design team can now see that there's going to be a slight issue. The original table and chair that we were going to use is too big now that we've got the doors in there, and we need to make a change to that. So we can either go in and make those changes manually and adjust the dimensions of the furniture, or in this case, what we have actually in this model is something called an interchange assembly. So maybe this is a modular table and chair set, and we have other options that we can swap in and out in that same location within this boat. So within the interchange assembly, something I'm going to talk a little bit more about in detail later on, we can swap this out for a different table and chair set, which now fits, coincidentally. So throughout advanced assembly, the reference view is something that can be really useful. I'm going to talk a little bit more about that in a second. But that's how we can work within context of a wider design and get visibility of what other users, what other teams are working on through the power of shrink wraps. Again, we're now going to have a look at another sort of approach, another technique for modeling up maybe the sleeping area for the crew. And this is something that's been sort of only really available for the more recent versions of Creo, and that's using multi-bodies within a skeleton design. So traditionally, it's always going to be 2D surfaces, 2D sketches, surfaces, datum planes. But now with the ability to generate multi-body components, we can now generate multi-body skeleton models. So we're in a skeleton model at the moment, and we're building up these different bodies within this one skeleton file. So here we've got a combination of both sheet metal and solid geometry, all in one part, in our skeleton part. And what we can now do once we've built up these defined bodies of information is we can save these out as components. So we can take this wall and we can generate a part from this body. And you get two options that you can see there. You've got copy, geometry, or inheritance. An inheritance feature, again, is an advanced assembly tool where we can create duplicates of components with the model history. Okay, so rather a linked model history rather than a save as, which will be a separate component completely. So we've created a separate component for that wall reinforcement there. We can also take these ladders for the bunk beds, and we're going to save this out as a component. And this multi-body approach really simplifies the assembly process because we can bring all these components back into the assembly and just assemble them to the default constraint, and they're going to overlap over the top of their multi-body skeleton. So it's a slightly different approach to a skeleton, leveraging these bodies within the skeleton, saving out those bodies as components and reassembling them back into your sub-assembly. So a few different approaches here. But again, it streamlines the process. We go back into our skeleton model, we make a change, we moves our body along, we come back to the top level assembly, regenerate, everything updates in position. So just a slightly different workflow that's become more available to users now we have the introduction of these multi-body components. So we talked about some different techniques within the advanced assembly process, working on this model, and that all accumulates then to making these larger scale design changes. Because of how we've logically shared information from that very top level, what we can now do is go and make a more major design change. So if I'm sort of the lead designer for this boat, I can come in and modify maybe some of the driving features that I want to modify, maybe the overall shape of the hull. I want to make changes to this. I can use our top level skeleton to come and make these changes. And because of how we've structured the rest of the model and shared that information intelligently along it, those design changes are going to trickle down through our model. Now, with any design changes and the references that get made within there, you can always expect some things to go wrong. So there are some tools and features we can use to help interrogate these. So as we go in and update this, we can see we've got a couple of outdated placement features, which are the manually updating copy geometries. But we've also got a sketch reference that's failing. So we can use the notification center to easily locate where that failure is. And then we've got various different techniques for interrogating failures and understanding them. So one of the really valuable ones is using something like the reference viewer, where you can go in and understand what the parent-child relationships are for a feature or a part within an assembly and understand what's going on. So here we can see that there are some missing references within the sketch. Maybe a reference plane has moved, or the angle has slightly changed, and the ID, maybe the curve has changed. So we can then go into the sketch, find the culprits and update them. So the reference view is really powerful for understanding how a model is being built, what references are being used within it, what relations maybe are driving those features. It's a really powerful tool for understanding designs, especially if you're coming into one that you've not worked on before, or you're coming back to an old design. So now we've fixed the sketch, we just have a couple of outdated references, which are manually updating copy geometries. So we can now go through and have a look at these and just update them. Again, using the notification center, we can easily find the corresponding feature that's failing. One thing I maybe want to mention in the tool set here, when you're looking at these show differences, we can obviously see the information that's changed, but from this, you may not always be able to understand what the downstream consequences of this are. If I update or accept this change, what's going to happen? It may make your model fall over. So one thing you can do is you can fire up an on-the-fly design exploration session. And what that is, it's basically like a safe environment. So it's going to open up a safe environment, it's going to apply the change, and you can interrogate it. So if it does fail, you can maybe understand what you need to change to fix that. Or what you could do is you could say, actually, no, okay, that's gone completely wrong. I'll back out, undo what I did in the skeleton and start again. Or once you fix the change in this session, you can commit that change down to your local model. So it's not something I'm showing in here, but that on-the-fly design exploration session can be really valuable for interrogating these designs, understanding them before committing to them completely. And we just have one final update to do here. So hopefully some of those techniques, you can start to see the power of how advanced assembly can really start to affect your workflow. It enables your different teams to all be working on their own areas of a design in isolation, but within context of an overall assembly, leveraging those skeleton models to share the critical design information down to those design teams and hang their geometry off of, therefore making it easier to come in and make these design changes through the use of skeletons, shared copy geometry, shrink wraps for working in context of other teams and designers and those sorts of things. So it's a really powerful design tool for working on these much larger and much more complex assemblies. So beyond the sort of methodology and the workflow, we also have managing the data itself, the amount of data that's on screen. How do we work? There's some tools and techniques that we can go into and have a look, and a couple of interest here. So if we are looking at working with large assemblies in maybe a smarter and more efficient way, there are a couple of different ways that affect the performance of that. And they break down into two key areas that affect performance when we're talking about career parameters. That's the amount of data that's loaded into the system, and then the amount of data that's actually on screen. And I think this has become less of a problem. With more powerful hardware, we can work on larger models, but our products are also getting slightly more complex. So to reduce the load on the system, we have a few tools that we can use to sort of aid with that. So we've got things like simplified representations for the amount of data that's loaded. And you saw some use of simplified representations throughout that demonstration, which were turning bits of component geometry on and off. So yeah, these allow you to, these simplified representations allow you to load in only the information that you're needed. So if we were working on this car that you can see on screen here, and I needed information from several different locations, maybe there are a few different sub-assemblies. Basically, it's the top level, but I don't need the bodywork. I don't need the interior seat locations. I just want sort of some of the drivetrain and some other bits and pieces. How do I open that up? Well, without it, you've just got to open up the whole model and then hide off what you don't need. But with a simplified representation, you can go in and pick and choose those elements from that top level that span multiple different sub-assemblies and components and parts. And just load that data in. So we don't have to load it all in, we can load a subset in. We also have our skeleton models, okay? And these are, as we've seen, a really good way of driving design information downstream. You don't have to have a whole model in session. You can just use the skeleton to hang your design off of. We talked about shrink wraps briefly. I'll show you how you can create one of those for sharing information from one location to another. I think shrink wraps are also really useful for working with third parties. I think that's become more apparent, especially as well of late. But when you're working with other suppliers, business partners, collaborating on designs, often you'll want to share some geometry with them so they can work around your design. Maybe the engine is being developed on. Maybe I designed the engine and the rest of the car is being designed by someone else. I need to give them a space claim. So we can use shrink wraps for creating a real lightweight piece of geometry that they can use in their designs. That also has all of my IP stripped out. None of that design information stored in that shrink wrap. It's a nice lightweight file they can use it to reference to and work around. So shrink wraps are really powerful. We then also have what data is then displayed on the screen. So how do we take control of those? We've got representations to help with that. We also have on-demand representations which update and dynamically change as we're working on them. And we've also got things like layer states for hiding components and showing different components on screen as well. So let's talk a little bit about simplified representations, because I don't think everyone is always aware of them. The first thing I'm going to mention is there are out of the box what we call simplified representations. So different versions of your model that you can open up out of the box within Creo. Now, PTC chose to hide a lot of these by default from Creo 4 onwards. I think that was primarily to simplify the onboarding process for new users. At the same time in Creo 4, PTC introduced this automatic rep, which is the default rep now in Creo. So whenever you open a model, it's opening the automatic rep, which is fundamentally the simplest version of the model it can open while giving you the most flexibility to work on it, because some of these other rep types don't allow you to work on your model in ways that you may expect it to. So PTC introduced this automatic rep, but they also hid off a few of these other rep types. So to turn that on, you need this hide pre-Creo 4 reps, and you need to set that to no. And then you get these other rep types available to us. So we've got this automatic rep, which is sort of the minimum amount of geometry it brings into the session for you to pretty much do anything you'd like on the model. We also have the master rep. So this was the old state, the old default state, and that just brings everything in. You can literally do anything with that. It's the full geometry, it's everything. We also have reps like the graphical rep, which basically just brings in the graphic information. There's no real geometry on there, which means you can't do things like mass property information, You can't always reference certain things in the graphical rep. It's just a visual representation of what the data looks like. The next level above that is a geometry rep, where it brings in the graphical information as well as some of the geometry. So you can do things like mass properties, you can explode your assemblies, those sorts of things. And they're just bringing in different amounts of data. So the graphics rep is going to be faster to open than the geometry rep, let's say. We also have something called the light graphics rep, which is something that's, I think, pretty underutilized, but it's incredibly quick at opening geometry. It looks a bit rubbish, but there are some useful uses for it, which I'm going to talk about in a bit of a demonstration. And then finally, down at the bottom there, there's another config option that I put in, which is open simplified rep by default. So when you just click the open dialog box in Creo, it just opens the model in the automatic rep. This config option will prompt you with a dialog box to choose a representation first. So either a graphics rep, master rep, whatever. And it just prevents users from opening the full geometry by default. You can pick and choose which ones you want to open by default. So just to give you a little bit of context and some stats, on screen here is a model that I've used for this example, which is about 2,000 components roughly. So it's a reasonable indication of a mid to large size assembly within Creo Parametric. Now, the master rep, that's everything, took 45 seconds to load. The automatic, and this is just on my machine here, obviously it will vary depending on your machine. The automatic rep there is 12 seconds. The light graphics rep, about a second. And that's about a second for pretty much any size model as well. It's extremely quick to bring in a light graphics representation. So I want to talk through some of those processes. So let's have a little look at these. So finding our model here, we can open up the light graphics representation. And what you can see on screen is a slightly bitty model, but 2,000 components opened up in about a second. This does have some uses. So there are things that we can do with this model. So even though it's a bit granular, what we can do is whenever you click on a component, it's going to drill down to the subassembly, the parts, the further subassembly, those sorts of things, until you get geometry. And then you can start interacting with it. So this is really useful if you want to come in and maybe do some interrogation on the overall design, maybe take some key design dimensions, those sorts of things. So you can work with this data, and it's extremely quick to open. So in here, I can come in and maybe I want to get a dimension on that front splitter. I can drill down till I find geometry that I can actually reference, and I can start making dimensional improvements on it. So real lightweight information loads up in a matter of no time, and I can start working on it. Another process I think it's really useful for is creating a design context. So when you're working on a model, and we talked about pulling in that overall assembly and using simplified representations to actually just pull in subsets, not all the data, the light graphics rep is a really nice way of defining what that simplified representation should be. So on the right hand side, you can see the default ones here. We've got the geometry rep, we've got our graphics rep, master rep, so those are some of the ones we talked about. We can create our own, and I'm actually going to create my own based on this light graphics data representation. So when we create our own, the usual model that we get presented with, the usual dialog you get presented with is this model tree on the left hand side. And I'm going to talk a little bit more about this in future. But you can actually pick and choose what elements you want in your representation from here. But instead, what I'm going to do, I'm going to leave a blank representation with nothing in it. And then I'm going to come back to my light graphics, which is already in session, and I can start picking and choosing elements. So here, I'm going to go drill down and grab the front wheel. I'm actually going to grab the rear axle as well. So just using a box select, I'm coming and pick geometry from my 3D model rather than a 2D interface. What you can see, if I let that media bar just hide, you can actually see down in the bottom right hand corner, just next to my filter selection, I've got 37 items selected. Now what's really cool is these selections remain active across representations. So now switching back to my design context that I was creating, that selection is still active. I can now change the representation type of those selected components to master, and it's going to load that information into my system. I can then save that representation, and that means next time I open my model, I could choose that design context as a representation I want to open and work on. So I now have the design data available to me to work on. And you can create as many of these simplified representations as you like. You're not restricted to just one or two. You can create them all at varying levels throughout your model, various different assemblies. Let me just jump back there. What I'm now doing, we've closed the model down, we're opening up another model. So I'm going to navigate to the top level, and I'm going to create an on-demand representation. So this is, again, just a different approach of generating a simplified rep. Rather than clicking open here, we've got the dialog box next to it, which we've probably seen but never maybe clicked on, which is open subset. What this enables me to do is open up the model structure before committing to what I'm opening. So here I have the full model structure. I can start picking and choosing what components I actually want to open from this master structure. So using the checkboxes, I can go through and pick and choose what elements I want. I can actually change the representation type as well. If I want to bring some light graphics in for a certain subassembly, I could do that. But what you can see now in the bottom left-hand side of the graphics window, you can see it's an on-demand representation. It's just created one on the fly for me. What I now want to do is talk through shrink wraps. So I'm working on this chassis, and I probably would have done this at the start, but it doesn't really matter. I want to understand how my chassis is going to work with the design team that's working on the transmission. So I want to have a representation of the transmission in my chassis here that I can work around as a bit of a space claim. I don't want to bring that data into my model. It's going to bog me down. It's just going to lock up the users that are trying to work on the transmission if I've got that data in session. So what I'm actually going to do is create a shrink wrap of the transmission. So using the shrink wrap feature, I can bring a real lightweight skinned version of the transmission into my model. You might want to do this in the skeleton model. In this instance, I'm simply just bringing it into the assembly. It doesn't really matter. But if it's in the skeleton, it wouldn't show up in a bill of materials, those sorts of things. So I've found the transmission assembly. I'm going to generate my shrink wrap. There are a few different techniques for generating these shrink wraps. In this case, I'm just creating a skin model, stripping out all the interior information, all the pistons, the valves, those sorts of things. It will do that automatically for me. And I now have sort of a visual representation of that data within my assembly that I can now work around. Check for things like interferences like we have here, make any design modifications. So these shrink wraps you can use from one assembly to another. You can also save out as a shrink wrap file. And that's really handy if you're collaborating with third parties. You can save out a shrink wrap of your model. They can then pull that into their own designs and have a real lightweight version of a model stripped out without your IP in it that they can use. We also talked very briefly, you saw in the demonstration with the boat where we swapped out the table and chair set with what we call an interchange assembly. Now, an interchange assembly serves as like a repository for similar components, and these components can then be swapped out with each other within a design. So it's great for configurable designs, or maybe you've got versions of a component that are manufactured in a slightly different way, and are really good for businesses that maybe operate into a more of a configure to order, or maybe an assemble to order process where you've got some user discretion on what components are being used and you need to swap these out within the design. So I thought it would just be worthwhile me highlighting, running through how we generate these interchange assemblies. They're part of the advanced assembly workflow. So let's have a quick look at this. Just hit play. So on this example, I've got a bracket on the yoke for the front forks on this bike. And maybe I've got, maybe it's different colors, different material options that users can have, or in this instance, there are a few different manufactured versions of this same bracket. And I want to be able to readily swap out these components for an assembly to generate maybe a bit of materials from, as an example. So rather than manually having to replace them each time, what I'm going to do, because these are very similar, I'm going to build what we call an interchange assembly. And an interchange assembly is basically a bucket. And I'm just going to dump all of these components that I want to swap out into this bucket, to which I can then swap out in my design. So the first thing to do is just bring in the original component. So we bring that into this design environment. And then we need to bring in the other manufactured items as well. So obviously I had one for an additive manufacturing process. I've got one for a milled manufacturing process, and one for a casting as well. So I'm going to bring these into my interchange assembly. That behaves slightly differently to a standard assembly. I'm not too concerned about where they are within this assembly, as long as I can see them on screen. That's absolutely fine. I don't need to worry about assembling them like you would a traditional assembly. They're just there. So these are the 4 components then that I wanted to be able to change to on my top level assembly. So we need to be able to swap these out, and in order to do that, we need to be able to reference these models within the assembly. So just having a look at the original design here, we can see there are 3 separate constraints that are used to define the location of that part in this assembly. So what we need to do is map those design constraints to all of these components. Now, the easiest way to do that is to choose the original part and go and pick up on the references that have been used in an assembly where that part has been used. In this case, it's going to be the front forks that we've used. So we'll open that up, and from that model, then we can determine what references have been selected on this component and where they map. We also then get dialog boxes for all of the other components that are in this interchange assembly. So it's just now a case of me mapping the references from the original to the new components. And there are a couple of different ways to do that. You can use this little drag handle and match the surfaces. Or a slightly quicker way, which we'll do next, is just holding control and clicking on the corresponding surfaces on the other components. So we're building in a load of design information into these components. We're making them more intelligent. So now I have my interchange assembly. What that means is I can go in and replace this component. You could just save that as another assembly. It behaves like any other assembly within your model. But when we do a replace, we can see interchange is available. I can find my interchange assembly, and I can pick a different component to swap out. Click OK. It's going to update automatically. You can actually have all of this information as well displayed in the model tree. So where you have an interchange assembly available, you can put in the model tree a little drop-down menu where you can easily just swap out those components. Not something I'm showing in here, but you can have those 3 different options in a drop-down next to the part in the model tree, and you just swap them out there. There's also a reference viewer to take a look at the information before you swap it out. But that's an interchange assembly. If you've got light components, obviously for 3 or 4, you could probably get away with just swapping those out manually. It doesn't take too much. But if you've got 100 different models that you're always swapping in and out, you get some real time savings when you're working with these interchange assemblies. Okay, so as we've seen, then AAX is really designed to help your engineering teams move faster, work smarter, and hopefully deliver better products. And there's a lot of value to be had. AAX helps you reduce things that are slowing your team down, whether that's communication, whatever it may be. You can cut your time to market by having that concurrent engineering, all your teams working together. You can lower development costs by eliminating rework and scrap and duplication of effort and those sorts of things. Your model complexity drops down because you have that logical sharing and intelligent sharing of data throughout your design. So in theory, your model complexity has been reduced. You get a better quality product, not just the item that rolls off the end of the line, but also in the actual engineering data you've created, which can have massive benefits in other departments, manufacturing, or if you're looking to expand your digital thread, leverage this data elsewhere. Having better engineering data itself is really, really useful. Innovation goes up. Your designers can explore more options because they've got the freedom to do so with these tools. Design efficiency again increases. Teams spend less time fixing problems, treading on other people's toes, working on other people's data. It frees everyone up. And you can build more configurable, more modular designs with the use of things like interchange assemblies as well. There are a whole host of other techniques as well that we just didn't quite have time to go through. There's another webinar that we've already run through on AAX, which you can find on demand as well. And that really focuses on some of the more specific tools. So some other tools like envelope reps and how we can swap out large components and those sorts of things. So again, that's available on demand. Do feel free to go back and have a look at those as well. I focus a little bit more maybe on the individual aspect. Here we focus very much on sort of teams, larger assemblies, but a lot of AAX techniques can be utilized on smaller models as well. There's a lot of value to be gained on simpler models as well. So thank you very much. As I said, we've got 2 more episodes coming up on the 4th and the 18th of June. So please do subscribe to those. You can do that on our website. And just to wrap things up, we'll have a look at some Q&A. But thank you very much for joining. If you need to rush off, but I will sit here and have a look at some questions. Okay, so why would I design let me just read this. So can I use multi-body over a skeleton as a traditional method? Not really. Multi-bodies are great for those sort of localized designs, and we did leverage a multi-body within a skeleton, but you can't replace AAX with multi-body design. There are communication techniques of how it doesn't really work at the assembly level. It works at the part level and sharing information out, but it doesn't really work at the assembly level. And you've got multiple teams working on different information. You need to be able to share that information logically across those teams. So no, multi-body doesn't really work at the scale of which you can use advanced assembly for. Is AAX available as a locked license? Yes, AAX is both available for locked and floating versions of the license type itself, as well as being able to opt for the T2 license as well. So if you want to upgrade the package, your Creo package, you can go for T2 or beyond, and that will include advanced assembly. If someone opens an assembly where AAX has been used, but they don't have the extension, what happens? That's a really, really good question. So yeah, if you've used something that's an AAX feature like copy geometry or publish geometry, and a user wants to work on that model but doesn't have that license, they will still be able to. So if you've got a part that's got geometry that's been copied into using the advanced assembly tools, that user can still work on that part if they don't have the license. What they can't do is go in and modify that copy geometry. So that copy geometry feature is an AAX feature. They can't modify that, but they can work on the other data. Do multi-bodies require the need for advanced assembly extension? No. So multi-bodies are part of standard Creo parametric functionality. So you can use those without AAX. What you couldn't do is what we did in the boat demonstration, where we had a multi-body part within a skeleton. A skeleton file is an advanced assembly file, so you couldn't do that. But you can use multi-bodies throughout Creo. Does the shrink wrap get updated when the original component gets updated? Yes, again, so you can control dependency between these two. So if you've created a shrink wrap feature that references the original, as and when that gets updated, that change can propagate through. A user will be notified that the change has been made, update the shrink wrap, and the shrink wrap will be updated. Or you could create a standalone item as a snapshot in time. You can also do that for the copy geometry features as well. So when we copy geometry maybe from one skeleton to another, we showed the automatic update where things just update automatically, as well as the manual update where users get to pick and choose as and when update. You can also choose a manual dependency, to break the dependency completely. So you copy geometry as a snapshot and you forget the original exists. So you've just got a snapshot in time there. Can users without AAX still constrain to the skeleton model? Yes, so this sort of goes back to one of the original, the other questions where users wanting to work on data that's been created using advanced assembly. Yes, you can assemble to a skeleton. So if you've got a skeleton model that's got some coordinate systems on it, which you're hanging components off of, again, a user in the assembly could assemble to those coordinate systems from the skeleton, and they just wouldn't be able to generate the skeleton itself. How do family tables interact with AAX? Are there something special you need to? It's a good question. I might need a little bit more detail on what your thought process is there. I might take that one offline. If you maybe just got a bit of context, or something you've got an idea of what you're trying to do there, if you could share that with me, I can take that one offline and get back to you all. What is the recommended representation for creating drawings? Ooh, that's a good question. Yeah, good question. I don't know off the top of my head. I guess it does depend on what you're trying to reference on those drawings. Dimensions and things, you probably get away with a lighter weight representation, but I might go away and confirm that with one of my colleagues on the drawing side. Yeah, I'll go away. I'll get back to that one. There might be something I'm missing on that. I'll come back to that one. My current version of Creo doesn't have the light rep, geometry rep, or graphic rep. Yes, so that's most likely due to the config option. If we rewind back through this model, so if you're not seeing some of these representations available, it's because PTC turned them off after Creo 4. So you need to set the config option, hide pre-Creo 4 reps, and set that to no. Once you set that to no, you should then be able to view these representation types when you open your models. One thing I didn't actually mention here was with the light graphics rep. You actually need the light graphics rep to be generated in order to open it. It's not something that happens by default. If you're connected to Windchill, Windchill should be generating these automatically, and you can get them from Windchill. If not, you can get Creo to generate them manually. Maybe in the Q&A sheet, I'll attach a little section there for a document that describes how to generate these light graphics representations. But yeah, you should be able to find these by setting this config option here. Okay, we're just overrunning now. So what I'll do, I'll take some of these, I'll take what I've been sent offline and document them all up for you, and we'll make sure we get those sent out. But thank you very much for joining. Hopefully you found it useful. If there are any further questions, pop them in the chat. We'll have someone to stick around and collect those. But yeah, thank you all very much. Hopefully you found it useful. I'll see you next time.